Yeah. So welcome everybody again to our geometric seminar, Gamma geometric seminar. And today is the second part of Xavier's talks about Lagrangian mechanics, hopefully time-dependent systems. So Xavi, the floor is yours. Please go ahead.
Thank you, Javi. Yeah, we will continue talking about Lagrangian mechanics. I will not be able probably to say anything about time-dependent systems, but what I will say is at least tell you 3 or 4 ways to geometrize time-dependent systems. These I will do it. I will tell you just very briefly, at least 3 or 4 strategies to do it. And maybe in a future talk, I will cover some of them. So let's continue, but to summarize what we were doing, we were focusing on the tangent bundle of a configuration manifold Q. And we were saying that we had some problems because when dealing with the Hamiltonian formalism, we worked in the cotangent bundle, and here we have some canonical structures, such as, for instance, a symplectic structure. And when we want to formalize Lagrangian mechanics, we need to do it in the tangent bundle. And here we do not have a canonical symplectic structure. Of course, we have many symplectic structures, but none of them is canonical. Maybe it's not global. So we have to do some things first, some tricks. Actually, we will build a symplectic structure out from a Lagrangian function defined on this tangent bundle. Of course, the two form that we will construct will not always be symplectic. Sometimes it will be pre-symplectic. But we will see that in many cases it is symplectic. So first, we need to introduce several canonical structures in the tangent bundle. We don't have a canonical symplectic form, but we have some canonical structures. So first of all, the vertical subbundle, we talked about this last session. We talked also about the vertical lift, and we saw that okay, we have this vertical lift, so that we can lift a vector from here to here, from the tangent bundle, from a tangent space at a point, the tangent space at a point of Q, to a tangent space to the tangent bundle of Q. And in natural coordinates, we can describe it if we pick a vector field in Q, a vector in Q at a point Q, we can lift it, and then we obtain this. This is a vertical. This is a vertical vector. That's why this is called a vertical lift. And of course, this can be extended to vector fields in Q. So we can lift a vector field in Q to a vertical field in TQ. And with all this, we are able to construct this canonical or vertical endomorphism here. And what's this? This is a map. Wait. Here, this is a map J going from the tangent space at a point QU of the fiber bundle TQ to itself. How? Just like this, by first projecting the vector downstairs and then lifting it vertically. Okay, so we go down and then we go up in a vertical way. So as I said, this is just the vertical lift of this projection to the point QU. As I said, we have to project and then lift vertically. This has many interesting properties. For instance, J squared equals 0, and thus we can define a short exact sequence. beginning with a vector, then we lift it, we transform it to a vertical vector field, and all the vertical vector fields, since we first project them, they go to 0. When we lift them, they go to 0 again. So vertical vector fields go to 0 through this map. So we have a map satisfying this, and this, of course, gives rise to a short exact sequence. This is what this proposition says. First of all, the image and also the kernel of this thing are the vertical vector fields, the vertical vectors. And of course, j squared equals to 0. Of course, we did it for vectors, but this can be extended. Actually, I already said it, to vector fields. We can extend this to vector fields, and we can also extend it to K forms. I will not be using this, but I think this is interesting. You can extend this canonical endomorphism not only to vector fields, but also to K differential forms. How? In this way. In this way, the J star acting on alpha is just the contraction of alpha with J. How? In this way. And in particular, in the case K equals 1 for 1 forms, this is just this composition here. Okay, this is just a 1 form satisfying this. These forms, the forms which are 0 by the action of vertical vector fields, are called tau semibasic. I will not be using this, but well, it's interesting that you know what semibasic forms are. Are those which are annihilated, let's say, by the action of vertical vector fields.
May I have a comment?
Yeah, sure.
Because here you have a tangent manifold, and attached to it you have a canonical endomorphism. Yeah. But one of the applications of canonical endomorphisms like mappings is to characterize a tangent bundle structure on a manifold. I mean, here from tangent manifold, you can define the canonical endomorphism. You will have also a so-called Euler vector field.
Yes. Next slide.
If I don't remember, I think as far as I remember, both structures allow you to define the tangent bundle structure.
Yes,
so,
you're absolutely right.
Yeah, so on any manifold, if you have two such mappings, generalize these two structures, canonical amorphism whose square is equal to 0 on tangent, along with one vector field with a 0 on belonging to the vertical space, to the kernel of the J, you can build up a tangent bundle structure.
Exactly. Actually, this canonical endomorphism is also called sometimes the tangent structure. And this is interesting, this thing you were saying, because if I'm not mistaken, your PhD advisor, Pepín Cariñena, has worked recently with these things. And I'm not sure exactly what he did. He did it with Miguel Muñoz.
I can't tell you what he did. It was about
let's try. Yeah. I think that he worked in things. So you have a second order differential equation, a vector field. I will tell you what it is in a couple of slides. If you multiply it by a function, it is no longer a second order differential equation, but it is a second order differential equation by changing the tangent structure, so changing this canonical endomorphism, and it is a SODE in another tangent structure. Is it what you were? Okay.
So he tried to tell me what he was going to do several months ago, and I told him to do so. I mean, it's the natural thing to do.
Yeah.
I mean, well, it's interesting. It's not about that he copied my idea. It's just that I think that it was a natural thing to do.
Yeah. I mean, I know this because Miguel grabbed me in a corridor and told me very fast. But the idea I had was this: so that in some way this this canonical endomorphism, you can change it and you obtain another tangent structure, giving you other dynamics and other things. This is interesting.
And this is
Okay.
just a last remark. You can do it.
Yes.
You can try to do something similar for bundles, for jet bundles.
Oh, interesting. With the Cartan distribution, I suppose.
Yeah, and K contact and things of the sort.
Oh, great. Okay. So in local coordinates, what does this thing look like? So taking natural adapted coordinates in the tangent bundle, this canonical endomorphism looks just like this. And in here, you can see how it turns any vector field in a vertical vector field, and how it turns any vertical vector field to 0. Okay, because when you contract this thing here, all the, let's say, if I have a vector field, ay partial qy plus vi partial vi, once I yeah, I don't know how to, okay, something like this, what I obtain is just this thing here. Okay, so of course any vector field goes to a vertical vector field, and any vector field, you can see this v does not longer appears here, so goes to 0. And last but not least, we have the Liouville vector field, the dilation vector field, or anything like this. This is a vector field, delta. It is vertical, and it is defined in this way. Okay, in natural coordinates, it looks just like this. This is the Liouville vector field. Sometimes I think it's also called the Euler vector field or the dilation vector field. You can find it with many names, but this is a natural structure in any tangent bundle. You can define it, of course, intrinsically like this, and in coordinates, it looks just like this. You can see that it is vertical. Okay, so what are the integral curves of this vector field? Okay, so curve is an integral curve of the Liouville vector field if it satisfies this system of differential equations, which is the solution of this system, this thing here. So as you can see, this is just the dilations along the fibers. Okay, it's the dilations on the fibers of the tangent bundle. Nothing more, nothing less. Okay, now with all these things, we will be able to introduce what we call second-order differential equations. And in differential geometry, everyone knows that a vector field in a manifold automatically defines a ODE, okay, or a system of ODEs. How? Well, in this way. You look for the curves satisfying this thing here. So every vector field defines a first-order system of differential equations. But we want to work with second-order differential equations because we are in mechanics, and we all know that the derivative of the position is the velocity, and it has to be like this. So we need to characterize those vector fields defining second-order differential equations, not first-order. We only will admit second-order differential equations. So we'll begin by defining what a holonomic curve is. A curve is holonomic, a curve in TQ. You see a curve, maybe this highlighter. Okay, a curve sigma in TQ is said to be holonomic if it is the lift of a curve in the base. In the last session, we defined this thing here. If we have a curve gamma in a manifold, we said how to define this gamma prime, which is the lift, and makes this diagram commutative. Okay, this is the canonical lift of the curve. So we will say that a curve in TQ, sigma, is holonomic if it is the canonical lift of a curve in the base. So in natural coordinates, what will a holonomic curve look like? It will look just like this, when the components in the fiber are just the derivatives of the q's, of the components of the curve, of the original curve. Okay, of course, every curve in TQ has associated a curve in Q. Okay, this is quite easy. I mean, we only have to project with the projection to the base space. In this way, a curve will be holonomic if and only if this equals to sigma. Okay, so projecting and then lifting, we obtain the original curve. In this case, then sigma is holonomic. And now what I was spoiling before, what are second order differential equations? Well, a second order differential equations, or a SODE, will be a vector field in TQ whose integral curves are holonomic. So we want our integral curve, the integral curve of our vector field, which will be the actual dynamics of the system, will have to be holonomic. So in natural coordinates, a SODE looks just like this, so that the components on the partial q's are just the velocities. What equation satisfy the integral curves of this vector field? The integral curves satisfy this second order differential equation here. And that's why we call this vector field second order differential equations, because they actually define second order differential equations. And now we are going to characterize these second order differential equations in several ways. If in coordinates a vector field looks like this, then it is second order differential equations. Also, if it satisfies this cool relation, I mean, if the canonical endomorphisms transforms my vector field to the Liouville vector field, then the original vector field was second order differential equation. And finally, if X, my vector field X, is a section of this projection here. This is something that you have to take into account. It was something, I mean, it looked tricky to me at the beginning, because when I began working with these things some years ago, of course, I knew that I have this projection here, but you can write your projection here and lift this canonical projection to TTQ. And what you have here is tau TQ. So this vector bundle has actually two different vector bundle structures, one given by the tangent of the canonical projection and the other given by the projection of this, thinking as the tangent bundle of the tangent bundle downstairs. So a vector field is a second order differential equation if it is a section of this projection. Okay, great. And now with all these geometric, let's say, tools, we are able finally to introduce Lagrangian dynamical systems. And in the same way as we did with the Hamiltonian systems, I will do it in an axiomatic way, so I can skip all the variational technicalities. Because I don't want to be talking about variational principles for an hour. And this way we can skip that. Maybe we can talk about that in another lecture. So in an axiomatic way, we will have several postulates for Lagrangian mechanics. First of all, the n degrees of freedom of a physical Lagrangian system are described by the domain of variation of a set of n generalized coordinates. these coordinates locally determine the configuration space of my system. And the states of the system are locally described by means of the corresponding generalized velocities. So what does this mean? Well, this means that the configuration space is a manifold Q, and the phase space or the state space is just the tangent bundle of Q. This is what this first postulate says. So, second postulate, the observables are the functions on TQ. This is just the same as in the Hamiltonian version. And another one, there exists a function, L, called the Lagrangian function, which contains all the dynamical information of the system. In this way, a pair TQ, a tangent bundle, and a function L is a Lagrangian dynamical system. This is a Lagrangian dynamical system, this pair, a tangent bundle and a Lagrangian function. I'm not talking about regular or singular Lagrangians at this point yet. Everything that I will do can be done for singular Lagrangians. When there are differences, I will say it. Okay.
May I have a
Yeah, sure.
remark? You know, these are postulates and they are said in many places. But one of the curious things is that they don't need to hold. I mean, there are examples, there are certain physical systems for which you will not have a Lagrangian function as it is to describe them. Yeah, it's kind of curious. It works pretty much well. That's why students learn this at the very beginning of their studies in physics because it's very useful. Mm-hmm. But these are postulates that do not need to hold. There are examples of systems where you cannot use these things. And there are generalizations too, many of you know, but it also happens there are certain differential equations appearing in physics that they are not known to be described, to be able to be described by means of Lagrangian functions or formalisms of the sort. You can find papers about it.
For instance, every time-dependent system is not described in this way.
Yeah, I mean, but even in the case of the obvious cases, because you're doing the time dependent.
I know
the time dependent is not.
Yeah.
There are several approaches to it, trying to make it as much general as possible.
Yeah, that's why here I said first postulate of Lagrangian mechanics. I mean, we only describe something that we call Lagrangian systems, which we don't know what a Lagrangian system is.
Yeah, is where it applies. Yeah.
We say Lagrangian systems will be the systems described by these postulates.
Yeah, the differential equations you obtain can be described by means of these formalisms. It's what I said about symplectic geometry and many other problems, that you have some differential equations and you are trying to describe them by means of certain formalisms. But
exactly,
they work. They are very good, but they are not perfect. Yeah, they're not. Okay, that's all. Thank you.
Yeah. Okay. So this is what I promised at the beginning of this lecture and at the end of the previous one. We are going to try to build a symplectic structure in a tangent bundle. How? With all the ingredients that we introduced. So given a Lagrangian function L, let's clear this a little bit. Given a Lagrangian function L on TQ, we will use this J, the canonical endomorphism, and the Liouville vector field to build several objects. First of all, the Cartan-1 form. What's the Cartan-1 form? It's just this thing here. It's this thing also, sometimes you will find it written in this way. Okay, you will find it sometimes in this way. This transpose is just the I mean, the J is a 1-1 tensor, so if you transpose it, you obtain a 1-1 tensor, but the other way around. So you can build this one form. You can build this one form just by transforming the differential of the Lagrangian with the canonical endomorphism, well, with the transposed of the canonical endomorphism J. The differential with a minus sign of this one form, this omega is the Cartan 2 form, and this will be, in favorable cases, our symplectic 2 form. Actually, the Cartan 1 form is the Liouville 1 form of the cotangent bundle. Well, it's not the Liouville 1 form, but will play the role of the Liouville 1 form in the cotangent bundle. And finally, we can construct a Lagrangian energy. This will be, let's say, this will be the theta, the one form in T star Q. This will be the omega, the true form in T star Q. And this will be the Hamiltonian, which is a function on T star Q. I mean, not exactly, but more or less, you have to think of these objects in this way, more or less analogously. So we can build our Lagrangian energy just by taking the derivative of the Lagrangian with the Liouville vector field minus the Lagrangian.
And by the way, may I have a remark about it?
Yeah, why not?
Because for students, one may think that this has been around for several centuries, but no, it did. That's the Cartan 1 form and the Cartan 2 form were developed. I'm not pretty much sure now, but maybe
second half of the 20s. Yeah,
it was by my supervisor in Salamanca, Pedro Luis Garcia. And it was with Rendon, and it was one of the professors when I was in Salamanca there.
Yeah, this was done in the 70s, probably.
Yeah, something of the sort. And this formalism was created at the same time with similar ideas by Pedro Luis, Rendon, and Gilbert Sternberg. I think all this stuff. And by the way, Pedro Luis is still alive.
But he's very old, right? He has to be 80.
Yeah, but he looks much better than you and I, probably. Yeah, he is maybe 80, 90 years old, something of the sort. Yeah, but he's perfectly and in perfect health. It is incredible. People used to say that makes some kind of agreement with the devil to
we can say that it's the differential geometry that keeps him alive.
Yeah, sure. Okay, that's all.
Yeah, it's a good advertisement to study differential geometry. Okay, so in coordinates, what do all these things look in coordinates? So we already know that the canonical endomorphism is this. This is the Liouville vector field. I will add also this thing here, because this is just, of course, the transposed. And okay, the Cartan 1 form looks like this. Of course, some of you may know a thing or two about Lagrangian and Hamiltonian mechanics in Rn. I mean, maybe some of you are familiar with these things. And some of you will know that this is the momenta somehow. So you can see that in coordinated somehow coincides with the Liouville 1 form. You have to be very careful here, because this is only true in some cases, okay? But very briefly, you can think of it like this, but I will erase this because it's not completely true that you can do this transformation always and back and forth. You cannot. The Cartan 2 form looks like this. It's just taking the exterior derivative with a minus sign of the 1 form. And this is just the Lagrangian energy, which corresponds somehow to the Hamiltonian function. So things that we have to see. For any Lagrangian function, the 2 form omega L is closed. Okay, so it is closed. But that's the thing. It's not always non-degenerate. So it's not always symplectic, but it is always pre-symplectic. This you have it always, but not always it will be non-degenerate. Okay? I will not be talking a lot
I
about the
may have
singular.
a comment.
Yeah, sure. Why not?
Normally, one technical one, okay? And the person
Okay.
sometimes about the fact that it's closed, but there is another detail. And the thing is that sometimes one requires it to have a kernel that has
Yeah,
a
constant
fixed
rank.
rank. But
Yes.
sometimes it is not that this cosymplectic when it's closed, and the kernel is a distribution with a fixed rank, I mean a regular distribution.
Yeah, you're right. Actually, the definition of
doesn't need to.
pre-symplectic is not very clear. I mean,
Yeah.
every author picks its definition. Every author picks a different definition of pre-symplectic, depending, especially on if you need this this distribution, the kernel, to have a constant rank. Sometimes they add an integrable distribution, which allows you to characterize some things. Okay.
The thing is that without these technical conditions, in most cases, or in many cases, you are not able to do anything.
No, you don't even have the root coordinates, as we know.
Yeah, for sure.
Yeah.
Do know that.
Yeah, but since I am not going to talk about singular systems in this talk, maybe in another one, I will not enter
Yeah,
the details of pre-symplectic manifolds. But just you have to know that it is always closed, okay, but it is not always non-degenerate. Sometimes it has degeneracy. And here we have the characterization of these Lagrangians. We will say that a Lagrangian L is regular, and thus this is a regular Lagrangian system if the true form is non-degenerate, and otherwise it is said to be singular. And this can be characterized in several ways, but the most important, maybe the most useful, is this one. This Hessian has to be invertible, has to be regular, okay? The Hessian of the Lagrangian with respect to the velocities has to be regular. There's another characterization for those who know more. A Lagrangian is regular if and only if the Legendre map going from here to here is a local diffeomorphism. This Legendre map is just the fiber derivative. It's just taking the derivatives along the fibers, only along the fibers. Locally, I can tell you what does it look like. Qi Vy, this goes to Qi, and taking the derivatives along the fibers, this thing here. So we can add another characterization here, which is that the Legendre map is a local diffeomorphism. This is a fourth way of saying the same thing. And I want to tell this because sometimes people talk about hyperregular Lagrangians. Okay, what are hyperregular Lagrangians? L is hyperregular if FL, the Legendre map, is a global diffeomorphism. And in this case, in the case of hyperregular Lagrangians, of course, we have a perfect correspondence between Hamiltonian and Lagrangian mechanics. Everything fits. In the case of regular Lagrangian, everything fits locally. And in the case of singular Lagrangians, many crazy things happen. Okay, I will not enter in the details of the singular case in this talk, as I've said many times. I will give you some examples of singular Lagrangians. Actually, I couldn't resist telling you about at the end of the last talk, and it provoked an interesting discussion about those Lagrangians. We'll see them once again today. And last postulate of Lagrangian mechanics. What's this postulate? It says that the dynamical trajectories of a Lagrangian system are the integral curves of a vector field such that what? It satisfies this equation, which of course corresponds somehow to this equation here in the Hamiltonian side. You can think of it as this in this way. That's why I said that this Lagrangian energy will play the role of the Hamiltonian. And this symplectic form, symplectic in the case of a regular Lagrangian, plays the role of the canonical symplectic form of the cotangent bundle. And in addition, we ask this Lagrangian vector field to be a second order differential equation. So to satisfy this condition. So these equations are called the Lagrangian equation for vector fields. A vector field solution to this equation is a Lagrangian vector field. And if it is a SODE, in addition, then it will be said an Euler-Lagrange vector field. So sometimes we will talk about Lagrangian vector fields or Euler-Lagrange vector fields, but most of the time we will always ask this SODE condition. And this is fun because in the regular case, we get this condition for free, as we will say right away. So a theorem, this relates the equations that satisfy the vector field and the integral curves. So a vector field is a Lagrangian vector field, that is, it is a solution. This means that this vector field satisfies this equation if and only if its integral curves are solutions to this. This is the Lagrangian equation for curves. And if the vector field is a SODE, the curves are holonomic. In local coordinates, let's see, because now we are going to obtain the Euler-Lagrange equation. So let's grab an arbitrary vector field and impose the Lagrangian equations. Imposing the Lagrangian equations in coordinates with a little work, you get to here. We obtain this. These are the Lagrangian equations in coordinates, but take a close look at this second equation. This second equation tells us a lot, and actually it tells us that if this is invertible, you can see that these coefficients here have to be Vy, because this has to be 0. So if the Lagrangian is regular, we obtain the SODE condition for free, because recall that every vector field with this local expression with more things here on the velocities is a SODE. So when the Lagrangian is regular, we obtain the second order condition for free. And substituting this upstairs in the first equation, this term vanishes, and we obtain these equations here. These are the Euler-Lagrange equations. Of course, for an integral curve satisfies.
May I have a question?
Yeah, sure.
Do you have any proof without coordinates?
Oh, that's an interesting question. Let me think. Maybe you could. I mean, a proof of what? Of that you get the SODE condition for free with regular Lagrange.
Yeah.
No, I don't. Well, wait, because you have that this has to satisfy this thing here, and you need to check this. No, I don't have one, but when the Lagrangian is hyperregular, you know that this is symplectic, so that given any function, you have a unique vector field here.
I believe you can, because the energy is defined with the endomorphism and the.
Oh yes.
And
So
using
the
that.
Potential of this thing here.
See, and you can start playing with that, and I think you can derive it.
Interesting.
I mean, that's the idea, but
Yeah, probably.
All the time I see the same proof all the time. I ask the same question, looking for someone who has done it. One day I have to do it on my own.
Well, it looks with this thing that Jordi said, it looks like a thing of Cartan calculus to do this.
Yeah, you know, what you have said is the usual stuff everyone does, because many things are very comfortable in coordinates. They look to be very easy to deal with. Yeah.
Yeah, but it is interesting, this thing you say.
Yeah, indeed, there are several proofs also in the Hamiltonian side. You try to do several things, and people used to do these things in coordinates because they are easy to do in coordinates.
Yeah.
There are other intrinsic manners, but people don't show them.
Yeah, are more tricky.
Yeah, they are more tricky, but they used to be more interesting. Sometimes they are more complicated, but we can learn something out of it.
Yeah, I agree. I mean, maybe we can continue with this thing here because this has to be
Right, also the form with the canonical
this thing here.
structures.
Yeah. We have to write the form on the other way, and this will be this contraction minus differential of wow, this is J transpose composed with DL. Well, I'm sure you can do it, but maybe we can do it at the end.
Yeah, but
We
by
can
the
open
way,
a blank slide and do the computations maybe in 5 minutes, but
yeah,
let's
by the
continue
way,
because if not, I will not be able to finish, and I want to.
okay.
The integral curves of the Euler-Lagrange vector field satisfy the Euler-Lagrange equations, which are these equations here. And for regular Lagrangians, we have that there exists a unique vector field solution to the equation, and it is always a second-order differential equation. So, some comments, okay? Some comments about these things. First of all, given a Lagrangian system, this triple here is a Hamiltonian system. Of course, it can be regular or singular. I didn't talk about singular Hamiltonian systems. Maybe I will in a future talk. And this will be depending only on the regularity of the Lagrangian. So in the regularity of the Hessian of the Lagrangian with respect to the velocities. So we can say that the Lagrangian formalism is a Hamiltonian formalism with some additional characteristics, such as the second order condition that we have to impose, but we get for free in the case of regular Lagrangians and so on. What about the singular case? This is the only thing I will say about singular systems today so that you can have an idea of what's going on here. So if the Lagrangian is singular, this is not a Hamiltonian system, a regular Hamiltonian system, but it is a pre-symplectic Hamiltonian system. And the Lagrangian equation, this here, may not be compatible everywhere. And of course, in the case that there's a solution, it may not be unique, nor a second order differential equation. So you lose almost everything. I mean, you may not have solution. If you have solution, it is not unique. If you have a solution, it is not a second order differential equation. And actually what happens is that if you have a solution, this is also a solution when you add everything in the kernel of this omega. This kernel might not even have constant rank. Maybe it has, maybe it doesn't. Depends on if you're asking for it or not. So in order to obtain the Euler-Lagrange equations, the Sode condition has to be imposed. You do not get it for free, but you can impose it, of course. So if we do not have solutions everywhere, what can we do? Okay, so we can implement what is known as a constraint algorithm. And how does this work? The idea is the following. First of all, you have to restrict yourself to a submanifold, if it is a submanifold, where you have solutions to your equation, to the Lagrangian equation. This equation, this equation here. You have to restrict the submanifold where you have solutions to this. But there's a problem. Maybe the solutions are in the submanifold but are not tangent to the submanifold. So you have to impose the tangency. When you impose the tangency of the solution to the submanifold, you might obtain additional constraints, defining maybe locally, maybe not, another smaller submanifold. Okay, so now we have a smaller submanifold and the solution, oh, yeah, the solution is tangent to the previous one, but not to this new one. So you have to impose a tangency again. You can do this one time and another until it stops. So until no new constraints appear. And in this case, you have found a smaller submanifold where you have solutions tangent to this submanifold, or maybe you don't. I mean, maybe you keep imposing constraints until you obtain only points or the empty set. Okay. And of course, you have to impose this Sode condition all the way. And this is the constraint algorithm. This is what you do when you have a singular Lagrangian. Of course, there are a lot of things to say about singular systems. There are papers and papers and papers talking about these algorithms, their geometric description. Of course, the first algorithms were not geometric, they were just in coordinates. This was all geometrized in the second half of the 20th century, 70s to 80s, what we were saying before. Okay, and now we will see a couple of examples just to finish. Let us consider again the harmonic oscillator. We considered it in the Hamiltonian side. We will consider it now in the Lagrangian side. So we have this function here, where m is the mass of the oscillator and k is the elastic constant. This is defined on the tangent bundle of the real line. So this is R2, nothing more, nothing less. And doing some computations, we found that this is the Lagrangian energy, this is the Liouville one form, and this is the Liouville, sorry, the Cartan one form and the Cartan two forms. This Lagrangian actually is regular, but it is not only regular, it is hyperregular. Okay, you can check it. And thus this thing here is a symplectic manifold. So if we have a symplectic manifold and we have a function playing the role of the energy, the Hamiltonian, let's say, we can build a Hamiltonian formalism, and this is what we do. We pick up a generic vector field, impose our equation. So with some computations, we find that this construction looks this way. I wanted to do this example very slowly so that you have at least one example completely done. But this is, of course, very easy. This is just computations. This is the differential of the Lagrangian energy. And thus, equating these things, the Lagrangian vector field looks like this. This is not only a Lagrangian vector field, this is the Euler-Lagrange vector field, because the Lagrangian is regular when we obtain the Sode condition just for free. Look that we didn't have to impose it as an additional requirement. We obtain it for free. And its integral curves satisfy this system of equations, which is actually a second order equation. We knew this because this vector field is holonomic, is a second order differential equation. And look that this is the equation of a harmonic oscillator. But in many cases, of course, in physics, Lagrangian functions usually have this form. Not only this form, because actually most of the time you will be dealing with Lagrangians which look this way, maybe with 1/2 here. This is a kinetic energy, okay, with a J being a G, sorry, being a Riemannian or pseudo-Riemannian metric. But in general, many Lagrangians will be of this type. These are called mechanical Lagrangians. But you can, of course, think of systems which are not described by mechanical Lagrangians, such as the examples that we introduced in the previous lecture. This example here that turns out that maybe it is even symplectic in some way, but it is for sure pre-symplectic with this Lagrangian here. It yields these equations which model a cold spreading in a population. This models a cold epidemic. There are more generalizations of this. Actually, you can generalize this to describe the SIR, the SIR system, which is a more complex system to describe epidemics or pandemics, as we all know for sure. And this Lagrangian, the Bailey Lagrangian, is actually singular because this is the Cartan 2 form which arises from this Lagrangian. And as you can see, this is singular because it has kernel. This is the kernel of this Lagrangian. Okay. Recall that we are here. We are on R2. So in the tangent bundle of R2, we have these coordinates x, y, x dot, y dot. So this true form is singular in this manifold here, in the tangent bundle of R2 plus, I mean the first, well, with x and y positive.
Just a fast remark for
sure,
Nikolai.
I was
Just,
missing your remarks.
Yeah, it was very quick. Omega L can be understood also as a differential two form on R2. As such, it will be singular because there are points where is not well defined when x, y are equal to 0. The point is, it can be understood in a certain way as a so-called symplectic form. That in short is a symplectic form that has some kind of singularity on a certain submanifold. And the thing is that the differential equation x dot y dot that it is written can be understood as a Hamiltonian vector field, as the differential equation for the integral cubes, a Hamiltonian vector field relative to this B symplectic form. It turns out that it is a so-called B Hamiltonian vector field. So somehow it is interesting for more than one reason. So that's
you will have for sure problems in the origin because it is not a submanifold at the origin. But yeah, if you remove the origin, of course you have a B symplectic.
Yeah, but there are things that can be done.
Yeah, sure, will be done. Okay, and another example. Let's say it is not different, but it is from another field. This comes from ecology, and it describes competitive equation, competitive species competing for the same resources. And yeah, it is described by this cool Lagrangian here, which is very singular. It is so singular that the Euler-Lagrange equations are not even second order. Okay, so the Euler-Lagrange equations are first order. Actually, this is the Euler-Lagrange equation for the variable y, and this is the Euler-Lagrange equation for the variable x. It is crossed. If you write the equations, this is the equation for y, and this is the equation for x. And again, this Cartan-2 form is pre-symplectic. It is no longer symplectic in the tangent bundle of R2 plus. And as you can see, this is a very strange Lagrangian. By the way, this D is a constant. Okay, this is not a differential. Okay, take this into account because maybe you can get confused. This is a parameter of the system. And with this, I finish what I wanted to say about Lagrangian mechanics. I have 3 minutes, so I will say a word or two. I left this slide blank, so I can write at least maybe 3 or 4 ways to write to describe time-dependent systems. So, very briefly, first way, if you want to check it out, you can look for papers. Cosymplectic geometry. This is the first idea. Using cosymplectic geometry, which is something that somehow generalizes. Well, not generalizes, it extends symplectic geometry. The canonical model will be not a cotangent bundle, but a cotangent bundle times the real line R. So we have always odd dimension. And we have that a cosymplectic structure is a manifold M with a 2 form and a 1 form tau. And well, the tau has to be 0, the omega has to be 0. Of course, this is a 2 form, this is a 1 form, and they have to satisfy this condition here. This has to be a volume form, and in this case, you have a Darboux theorem. I'm going very fast, but if you want to look for information about this, you can. And if you want me to explain it, I can give a lecture only on cosymplectic geometry, on cosymplectic systems, if you are interested in it. So you can find Darboux coordinates so that this tau is just the differential of the time. Of course, you can think of this real line as the time, and omega will be dqi dpy. And here you can write the Hamilton equations. The only thing that you have is that this thing has to be the differential of the Hamiltonian, and this thing here has to be 1. And these are, what did I? Okay, and these are the Hamiltonian equations for cosymplectic systems. There are other approaches. I will not talk about them a lot, but you can use contact geometry also. lately, contact geometry is being used to describe non-conservative systems, but before that, it was used to describe time-dependent systems in a different way, of course, but the additional coordinate that you have, because in contact manifolds, you have always 2n+1 dimensions, you can use somehow this as a time and build a formalism using contact manifolds to describe time-dependent, no conservative, but okay, I think you get the point. Time-dependent system, but not with the dissipations you usually associate with contact, but only with time dependence. In addition, you can use something which is called the extended symplectic formalism or something like that, extended symplectic, which is say, okay, this is my configuration manifold, right? Yes. If I want to include the time, why don't just multiplying by r? So my phase space will be this thing here. And this thing here has a virtue. This is symplectic. Okay, well, this is symplectic in the case you have a Lagrangian and everything works. But this is even dimensional. So this has the potential to be symplectic. And you can use all the symplectic things that we know in order to build a formalism for time-dependent systems here. And of course, there's a fourth approach, which is used sometimes. I think, Javi, you have worked with this, which is thinking T as a parameter. Okay, so that you have T vector fields. Am I right, Javi?
Yep.
Okay, so you can work with this also. You can think of time as a parameter and have a T-dependent vector field. So vector fields in your manifold, you have your manifold Q, you have a vector field which, instead of depending only on the Qs, it also depends on T. And you have something like this. And you can work in this way also. So it's time, it's 10. Okay, so this is everything I wanted to say. Well, I wanted to say more, but I will say it probably in a future lecture. I will talk about these time-dependent systems. Also, I can talk about singular systems. I mean, I've opened many topics, and for sure, me or someone else can cover them in future lectures. So if you have any questions, remarks, counterexamples, anything?
Yeah, are these approaches equivalent?
Yeah, I think so. I haven't worked with all of them. I've worked mostly with the cosymplectic one, but I think they are. Yeah,
they are not equivalent.
No, they are not, Javi.
No. For example, at least the T-dependent approach has the problem that third time symmetries, for example, of systems, they are partially in terms of time, and the problem is that when the time is a parameter, you cannot deal with these things. So you need Albert extended, Albert the contact geometry approach.
Oh, interesting. Well, I didn't know about this. Well, I don't know a lot about this thinking of the time as a parameter. I always introduce it as a dimension in the manifold somehow.
I mean, the problem is that it can be a parameter, but there is no partial time on terms of the time. In this approach. When you pick up the partial on terms of time or differential of time, everything that depends on it cannot be fixed, cannot be used in the time dependent parameter.
Yeah, you're right.
It's not well. So you need all the contract, all the standard symplectic or cosymplectic also, yeah.
And they are not
yeah, Jordi.
They are not equal in a more global sense. For instance, the Jacobi structure of contact and cosymplectic is not exactly the same.
Yeah,
There's some global.
Yeah, they are equivalent in the sense that you obtain the Hamiltonian equations, which are, of course, the equations obtained from the variational principle. So you obtain the same equations, but of course, the geometry, the underlying geometry is not the same. That's true.
So sometimes, well, they don't need to be the same. There must be some way of relating both.
Yeah.
But there is no, in general, there is no such a way.
Any more questions or comments? No.
I
Okay.
have a question. It's rather a light question, but I was wondering whether the in cosymplectic geometry
Yes.
implies any duality with respect
No.
to symplectic geometry, or rather, is it perhaps somewhat related to contact geometry, where you have, I think, some common notions like Reeb vector fields in both?
Yeah, it is for sure not a duality. Symplectic geometry is always even dimensional. Cosymplectic geometry is always odd dimensional. And we can say maybe a thing or two about contact. A contact manifold, okay, let's say a co-oriented contact, a co-oriented contact manifold is a pair M eta, where eta is a one form, but this one form satisfies this condition here. This has to be a volume form, this thing here, and this is quite similar to this condition here, as you said, but it is not exactly the same, because even in the case that you say, okay, let's say that this omega is this theta here, well, this is not possible, okay, because here the tau cannot be the eta, because this tau is closed and this eta is not closed. So they are not exactly the same. They are both odd dimensional, but they are not equivalent in any way.
There is a nice way of passing from one to the other. For example, when you have the cosymplectic, and you have the omega, that is presymplectic form with a kernel that is one-dimensional.
Yeah, actually, wait. The kernel is generated by the rep vector field.
Yeah, the thing is that this omega is closed. So you have potential. You have a certain one form whose differential is omega.
Yes.
If you pick up this form, at least locally, yeah, and you add this form to the tau, to the one form, okay, you will get a contact manifold. So you can do it in this way.
Oh,
And
interesting.
so they are related. Also with the contact, you can do a similar thing, and you can, when you have d eta, you know how it was. No. We're speaking about, there is a method to go from one to another. The problem is that it works for the structure, but as far as I remember, it does not work for Hamiltonian vector fields. There is no way of passing from one to the other. So while geometries are related between them, the problem is that Hamiltonian systems and in one approach and the other, they seem to be at least different and not treatable at the same time. So this is one of these cases when geometric structures are related, but the formalist is not equivalent. Yeah, it doesn't matter whether you can go for a cosymplectic to a contact or a contact to a cosymplectic, whatever. The thing is, even if you are able to go from one to the other, yeah, the things that are described in one approach and the other approach cannot be described in an equivalent or similar way.
Well, there's a thing here, Javi, because as I said, you can use contact geometry to describe time-dependent systems, and actually you can find a suitable contact structure in here, which is not the canonical one, which gives you the Hamiltonian, whose Hamiltonian vector field coincide with the Hamiltonian vector field in the cosymplectic case, so that you get the time-dependent dynamics. But you have to look for other contact structures here. Maybe I can tell you which contact structure. I don't have it here. Maybe I can tell you another day.
It could be that would be very interesting indeed.
Yeah, I can tell you another day. Any more questions, comments? No. Okay, so time for an announcement. Oh, wait. Time for a little announcement. Next week, Jordi will be speaking about the geometry of field theory. So we will meet next Thursday, 4th of May at 9 p.m. as usual. So I think that's all. Javi, you want to
Thank
say
you.
anything?
No, I have no more remarks. Is any other question, remark, comment? Saying that we don't like Xavi? No? Okay. Thank you again, Xavi, for everything, for a nice talk.
Thank you.
Thank you.
So see you all next Thursday.
Yeah, good night.
Good
Good
night.
night.
Dobranoc.